The charges of protons and electrons are equal in magnitude but opposite in polarity, so when these two particles are paired, the charges cancel each other out. Since matter typically contains equal numbers of positively charged protons and negatively charged electrons, most substances are electrically neutral. Illustrations sometimes show electrons orbiting the nucleus in a manner that resembles the planets of our solar system orbiting the Sun. However, electrons do not actually behave this way. A more realistic depiction would show electrons as a cloud of negative charges surrounding the nucleus. Studies of the arrangements of electrons show that they move about the nucleus in regions called principal shells, each with an associated energy level. In addition, each shell can hold a specific number of electrons, with the outermost shell generally containing valence electrons. These electrons can be transferred to or shared with other atoms to form chemical bonds. Most of the atoms in the universe were created inside massive stars by nuclear fusion and then released into interstellar space during hot, fiery supernova explosions. As this ejected material cooled, the newly formed nuclei attracted electrons to complete their atomic structure. At the temperatures found at Earth's surface, free atoms generally have a full complement of electrons, one for each proton in the nucleus. Elements, defined by their number of protons. The simplest atoms have only one proton in their nuclei, whereas others have more than 100. The number of protons in the nucleus of an atom, called the atomic number, determines its chemical nature. All atoms with the same number of protons have the same chemical and physical properties. Collectively, they constitute an element. There are about 90 naturally occurring elements, and several more have been synthesized in the laboratory. You are probably familiar with the names of many elements, including carbon, nitrogen, and oxygen. All carbon atoms have 6 protons, whereas all nitrogen atoms have 7 protons, and all oxygen atoms have 8. The periodic table, shown in Figure 3.5, is a tool scientists use to organize the known elements. In it, elements with similar properties line up in columns, referred to as groups. Each element is assigned a 1- or 2-letter symbol. The atomic number and atomic mass for each element are also included in the periodic table. Figure 3.5 Periodic Table of the Elements. Figure 3.5 Full alternative text description. Did you know? The purity of gold is expressed by the number of carats. 24 carats is pure gold. Gold less than 24 carats is an alloy of gold and another metal, usually copper or silver. For example, 14-karat gold contains 14 parts gold mixed with 10 parts of other metals. Atoms of the naturally occurring elements are the basic building blocks of Earth's minerals. Most elements join with other elements to form chemical compounds. Therefore, most minerals are chemical compounds composed of atoms of 2 or more elements. These include the minerals quartz, halite, and calcite caco. However, a few minerals, such as diamonds, sulfur, and native gold and copper, are made entirely of atoms of only one element. Concept checks 3.2. Figure 3.6 Examples of minerals composed of a single element. 1. Make a simple sketch of an atom and label its 3 main particles. Explain how these particles differ from one another. 2. What is the significance of valence electrons? 3.3 Why atoms bond. Distinguish among ionic bonds, covalent bonds, and metallic bonds. Under the temperature and pressure conditions found on Earth, most elements do not occur in the form of individual atoms. Instead, their atoms bond with other atoms. Some atoms bond to form ionic compounds, some form molecules, and still others form metallic substances. Why does this happen? Experiments show that electrical forces hold atoms together and bond them to each other. These electrical attractions lower the total energy of the bonded atoms, and this, in turn, generally makes them more stable. Consequently, atoms that are bonded in compounds tend to be more stable than atoms that are free. The octet rule and chemical bonds. As noted earlier, valence electrons are generally involved in chemical bonding. Figure 3.7 shows a shorthand way of representing the number of valence electrons for some selected elements. Notice that the elements in group I have 1 valence electron, those in group 2 have 2 valence electrons, and so on, up to 8 valence electrons in group 8. Each dot represents a valence electron found in the outermost principal shell. Figure 3.7 Full alternative text description. The noble gases have very stable electron arrangements with 8 valence electrons and, therefore, tend to lack chemical reactivity. Many other atoms gain, lose, or share electrons during chemical reactions, ending up with electron arrangements of the noble gases. This observation led to a chemical guideline known as the octet rule. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Although there are exceptions to the octet rule, it is a useful rule of thumb for understanding chemical bonding. Figure 3.7. Diagrams for certain elements. When an atom's outer shell does not contain 8 electrons, it is likely to chemically bond to other atoms to achieve an octet in its outer shell. A chemical bond is a transfer or sharing of electrons that allows each atom to attain a full valence shell of electrons. Some atoms do this by transferring all their valence electrons to other atoms so that an inner shell becomes the full valence shell. When the valence electrons are transferred between the elements to form ions, the bond is an ionic bond. When the electrons are shared between the atoms, the bond is a covalent bond. When the valence electrons are shared among all the atoms in a substance, the bonding is metallic. Ionic bonds, electrons transferred. Perhaps the easiest type of bond to visualize is the ionic bond, in which one atom gives up one or more valence electrons to another atom to form ions, positively and negatively charged atoms. The atom that loses electrons becomes a positive ion, and the atom that gains electrons becomes a negative ion. Oppositely charged ions are strongly attracted to one another and join to form ionic compounds. Consider the ionic bonding that occurs between sodium and chlorine. To produce the solid ionic compound sodium chloride, the mineral halite. Notice in Figure 3. 8a that a sodium atom gives up its single valence electron to chlorine and, as a result, becomes a positively charged sodium ion. Chlorine, on the other hand, gains one electron and becomes a negatively charged chloride ion. We know that ions having unlike charges attract. Thus, an ionic bond is an attraction of oppositely charged ions to one another that produces an electrically neutral ionic compound. Figure 3.8 Full alternative text description. Figure 3.8 Formation of the ionic compound sodium chloride. Figure 3.8b illustrates the arrangement of sodium and chlorine ions in ordinary table salt. Notice that salt consists of alternating sodium and chlorine ions, positioned so that each positive ion is attracted to and surrounded on all sides by negative ions and vice versa. This arrangement maximizes the attraction between ions with opposite charges while minimizing the repulsion between ions with identical charges. Thus, ionic compounds consist of an orderly arrangement of oppositely charged ions assembled in a definite ratio that provides overall electrical neutrality. The properties of a chemical compound are dramatically different from the properties of the various elements comprising it. For example, sodium is a soft silvery metal that is extremely reactive and poisonous. If you were to consume even a small amount of elemental sodium, you would need immediate medical attention. Chlorine, a green poisonous gas, is so toxic that it was used as a chemical weapon during World War I. Together, however, these elements produce sodium chloride, the harmless flavor enhancer that we call table salt. Thus, when elements combine to form compounds, their properties change significantly. Covalent bonds, electron sharing. Sometimes the forces that hold atoms together cannot be understood on the basis of the attraction of oppositely charged ions. One example is the hydrogen molecule, in which the two hydrogen atoms are held together tightly and no ions are present. The strong attractive force that holds two hydrogen atoms together results from a covalent bond, a chemical bond formed by the sharing of one or more valence electrons between a pair of atoms. Imagine two hydrogen atoms approaching one another, as shown in figure 3.9. Once they meet, the electron configuration changes so that both electrons primarily occupy the space between the atoms. In other words, the two electrons are shared by both hydrogen atoms and are attracted simultaneously by the positive charge of the proton in the nucleus of each atom. In this situation, the hydrogen atoms do not form ions. Instead, the force that holds these atoms together arises from the attraction of oppositely charged particles, positively charged protons in the nuclei and negatively charged electrons that surround these nuclei. When hydrogen atoms bond, the negatively charged electrons are shared by both hydrogen atoms and attracted simultaneously by the positive charge of the proton in the nucleus of each atom. Figure 3.9 Formation of a covalent bond. Figure 3.9 Full alternative text description. Metallic bonds, electrons free to move. A few minerals, such as native gold, silver, and copper, are made entirely of metal atoms packed tightly together in an orderly way. The bonding that holds these atoms together results from each atom contributing its valence electrons to a common pool of electrons, which freely move throughout the entire metallic structure. The contribution of one or more valence electrons leaves an array of positive ions immersed in a sea of valence electrons, as shown in figure 3.10. Metallic bonding is the result of each atom contributing its valence electrons to a common pool of electrons that are free to move throughout the entire metallic structure. The attraction between the sea of negatively charged electrons and the positive ions produces the metallic bonds that give metals their unique properties. Figure 3.10 Full alternative text description. The attraction between this sea of negatively charged electrons and the positive ions produces the metallic bonds that give metals their unique properties. Metals are good conductors of electricity because the valence electrons are free to move from one atom to another. Metals are also malleable, which means they can be hammered into thin sheets, and ductile, which means they can be drawn into thin wires. By contrast, ionic and covalent solids tend to be brittle and fracture when stress is applied. Consider the difference between dropping a metal frying pan and a ceramic plate onto a concrete floor. Figure 3.10 Metallic bonding. Concept checks 3.3. 1. What is the difference between an atom and an ion? 2. How does an atom become a positive ion? A negative ion? 3. Briefly distinguish between ionic, covalent, and metallic bonding and discuss the role that electrons play in each. 3.4 Properties of minerals. List and describe the properties used in mineral identification. Minerals have definite crystalline structures and chemical compositions that give them unique sets of physical and chemical properties shared by all specimens of that mineral, regardless of when or where they formed. For example, 2 samples of the mineral quartz will be equally hard and equally dense, and they will break in a similar manner. However, the physical properties of individual samples may vary within specific limits due to ionic substitutions, inclusions of foreign elements, and defects in the crystalline structure. Some mineral properties, called diagnostic properties, are particularly useful in identifying an unknown mineral. The mineral halite, for example, has a salty taste. Because so few minerals share this property, a salty taste is considered a diagnostic property of halite. Other properties of certain minerals, particularly color, vary among different specimens of the same mineral. These properties are referred to as ambiguous properties. Optical properties. Of the many diagnostic properties of minerals, their optical characteristics such as luster, color, streak, and ability to transmit light are most frequently used for mineral identification. Luster. The appearance or quality of light reflected from the surface of a mineral is known as luster. Minerals that are shiny like a metal, regardless of color, are said to have a metallic luster. Some metallic minerals, such as native copper and galena, develop a dull coating or tarnish when exposed to the atmosphere. Because they are not as shiny as samples with freshly broken surfaces, these samples are often said to exhibit a submetallic luster. Figure 3.11 Metallic versus submetallic luster. Figure 3.11 Full alternative text description. Most minerals have a non-metallic luster and are described using various adjectives. For example, some minerals are described as being vitreous or glassy. Other non-metallic minerals are described as having a dull or earthy luster or a pearly luster. Still others exhibit a silky luster or a greasy luster. Color. Although color is generally the most conspicuous characteristic of any mineral, it is considered a diagnostic property of only a few minerals. Slight impurities in the common minerals fluorite and quartz, for example, give them a variety of tints, including pink, purple, yellow, white, gray, and even black. Other minerals, such as tourmaline, also exhibit a variety of hues, with multiple colors sometimes occurring in the same sample. Thus, the use of color as a means of identification is often ambiguous or even misleading. Some minerals, such as fluorite shown here, exhibit a variety of colors. Streak. Smart Figure 3.12 Color variations in minerals. Watch tutorial, Mineral color. The color of a mineral in powdered form, called streak, is often useful in identification. A mineral streak is obtained by rubbing it across a streak plate and observing the color of the mark it leaves. Although a mineral's color may vary from sample to sample, its streak is usually consistent in color. Smart Figure 3.13 Streak. Watch video, Mineral streak. Streak can also help distinguish between minerals with metallic luster and those with non-metallic luster. Metallic minerals generally have a dense, dark streak, whereas minerals with non-metallic luster typically have a light-colored streak. Ability to transmit light. Another optical property used to identify minerals is the ability to transmit light. When no light is transmitted through a mineral sample, that mineral is described as opaque. When light, but not an image, is transmitted, the mineral is said to be translucent. When both light and an image are visible through the sample, the mineral is described as transparent. Crystal shape, or habit. Mineralogists use the term crystal shape, or habit, to refer to the common or characteristic shape of individual crystals or aggregates of crystals. Some minerals tend to grow equally in all three dimensions, whereas others tend to be elongated in one direction or flattened if growth in one dimension is suppressed. The crystals of a few minerals can have a regular polygonal shape that is helpful in identification. For example, magnetite crystals sometimes occur as octahedrons, garnets often form dodecahedrons, and halite and fluorite crystals tend to grow as cubes or near cubes. Most minerals have just one common crystal shape, but a few, such as the pyrite samples shown in Figure 3.14, have two or more characteristic crystal shapes. Figure 3.14 Common crystal shapes of pyrite. Did you know? The name crystal is derived from the Greek and was originally applied to quartz crystals. The ancient Greeks thought quartz was water that had crystallized at high pressures deep inside Earth. In addition, some mineral samples consist of numerous intergrown crystals exhibiting characteristic shapes that are useful for identification. Terms commonly used to describe these and other crystal habits include equant, bladed, fibrous, tabular, cubic, prismatic, platy, blocky, and banded. Some of these habits are pictured in Figure 3.15. A. Thin, rounded crystals that break into fibers. B. Elongated crystals that are flattened in one direction. C. Minerals that have stripes or bands of different color or texture. D. Groups of crystals that are cube-shaped. Smart Figure 3.15 Some common crystal habits. Smart Figure 3.15 Full alternative text description. Mineral strength. Watch tutorial, mineral habit. How easily minerals break or deform under stress is determined by the type and strength of the chemical bonds that hold the crystals together. Mineralogists use terms including hardness, cleavage, fracture, and tenacity to describe mineral strength and how minerals break when stress is applied. Hardness. One of the most useful diagnostic properties is hardness, a measure of the resistance of a mineral to abrasion or scratching. This property is determined by rubbing a mineral of unknown hardness against one of known hardness or vice versa. A numerical value of hardness can be obtained by using the Mohs scale of hardness, which consists of 10 minerals arranged in order from 1 to 10, as shown in Figure 3. 16a. It should be noted that the Mohs scale is a relative ranking and does not imply that a mineral with a hardness of 2, such as gypsum, is twice as hard as mineral with a hardness of 1, like talc. In fact, gypsum is only slightly harder than talc, as Figure 3.16b indicates. A. The Mohs scale of hardness, with the hardness of some common objects. B. Relationship between the Mohs relative hardness scale and an absolute hardness scale. Smart Figure 3.16 Hardness scales. Smart Figure 3.16 Full alternative text description. Watch tutorial, mineral hardness. In the laboratory, common objects used to determine the hardness of a mineral can include a human fingernail, which has a hardness of about 2.5, a copper penny, and a piece of glass. The mineral gypsum, which has a hardness of 2, can be easily scratched with a fingernail. On the other hand, the mineral calcite, which has a hardness of 3, will scratch a fingernail but will not scratch glass. Quartz, one of the hardest common minerals, will easily scratch glass. Diamonds, hardest of all, scratch anything, including other diamonds. Cleavage. In the crystal structure of many minerals, some atomic bonds are weaker than others. It is along these weak bonds that minerals tend to break when they are stressed. Cleavage is the tendency of a mineral to break along planes of weak bonding. Not all minerals have cleavage, but those that do can be identified by the relatively smooth, flat surfaces that are produced when the mineral is broken. The simplest type of cleavage is exhibited by the micas. Because these minerals have very weak bonds in one direction, they cleave to form thin, flat sheets. Some minerals have excellent cleavage in 1, 2, 3, or more directions, whereas others exhibit fair or poor cleavage, and still others have no cleavage at all. When minerals break evenly in more than one direction, cleavage is described by the number of cleavage directions and the angle at which they meet. The thin sheets shown here exhibit one plane of cleavage. Smart Figure 3.17 Micas exhibit perfect cleavage. Watch animation, types of cleavage. Smart Figure 3.18 Cleavage directions exhibited by minerals. Smart Figure 3.18 Full alternative text description. Each cleavage surface that has a different orientation is counted as a different direction of cleavage. For example, some minerals, such as halite, cleave to form 6-sided cubes. Because cubes are defined by three different sets of parallel planes that intersect at 90-degree angles, cleavage for the mineral halite is described as three directions of cleavage that meet at 90 degrees. Watch tutorial, Mineral Cleavage. Do not confuse cleavage with crystal shape. When a mineral exhibits cleavage, it breaks into pieces that all have the same geometry. By contrast, the smooth-sided quartz crystals shown in Figure 3.1 do not have cleavage. If broken, they fracture into shapes that do not resemble one another or the original crystals. Fracture. Minerals having chemical bonds that are equally, or nearly equally, strong in all directions exhibit a property called fracture. When minerals fracture, most produce uneven surfaces and are described as exhibiting irregular fracture. However, some minerals, including quartz, sometimes break into smooth, curved surfaces resembling broken glass. Such breaks are called conchoidal fractures. Still other minerals exhibit fractures that produce splinters or fibers referred to as splintery fracture and fibrous fracture, respectively. Figure 3.19 Irregular versus conchoidal fracture. Tenacity. The term tenacity describes a mineral's resistance to breaking, bending, cutting, or other forms of deformation. As mentioned earlier, nonmetallic minerals such as quartz and minerals that are ionically bonded, such as fluorite and halite, tend to be brittle and fracture or exhibit cleavage when struck. By contrast, native metals, such as copper and gold, are malleable, which means they can be hammered without breaking. In addition, minerals that can be cut into thin shavings, including gypsum and talc, are described as sectile. Still others, notably the micas, are elastic and bend and snap back to their original shape after stress is released. Did you know? The mineral pyrite is commonly called fool's gold because its golden yellow color closely resembles gold. The name pyrite is derived from the Greek pyros because it gives off sparks when struck sharply. Density and specific gravity. Density, an important property of matter, is defined as mass per unit volume. Mineralogists often use a related measure called specific gravity to describe the density of minerals. Specific gravity is a number representing the ratio of a mineral's weight to the weight of an equal volume of water. Most common minerals have a specific gravity between 2 and 3. For example, quartz has a specific gravity of 2.65. By contrast, some metallic minerals, such as pyrite, native copper, and magnetite, are more than twice as dense and thus have more than twice the specific gravity of quartz. Galena, an ore from which lead is extracted, has a specific gravity of roughly 7.5, whereas 24-karat gold has a specific gravity of approximately 20. With a little practice, you can estimate the specific gravity of a mineral by hefting it in your hand. Does this mineral feel about as heavy as similarly sized rocks you have handled? If the answer is yes, the specific gravity of the sample will likely be between 2.5 and 3. Other properties of minerals. In addition to the properties discussed thus far, some minerals can be recognized by other distinctive properties. For example, halite is ordinary salt, so it can be quickly identified through taste. Talc and graphite both have distinctive feels. Talc feels soapy, and graphite feels greasy. Further, the streaks of many sulfur-bearing minerals smell like rotten eggs. A few minerals, such as magnetite, have high iron content and can be picked up with a magnet, while some varieties are themselves natural magnets and will pick up small iron-based objects such as pins and paper clips. Moreover, some minerals exhibit special optical properties. For example, when a transparent piece of calcite is placed over printed text, the letters appear twice. This optical property is known as double refraction. This sample of calcite exhibits double refraction. Figure 3.20 Double refraction. One very simple chemical test to detect carbonate mineral involves placing a drop of dilute hydrochloric acid from a dropper bottle onto a freshly broken mineral surface. Samples containing carbonate minerals will effervesce as carbon dioxide gas is released. This test is especially useful in identifying calcite, a common carbonate mineral. Smart Figure 3.21 Calcite reacting with a weak acid. Concept checks 3.4. 1. Define luster. 2. Why is color not always a useful property in mineral identification? Give an example of a mineral that supports your answer. 3. What differentiates cleavage from fracture? 4. What is meant by a mineral's tenacity? List 3 terms that describe tenacity. 5. Describe a simple chemical test that is useful in identifying the mineral calcite. Watch video, calcite reacting to acid. 3.5 Mineral groups. Explain how minerals are classified and name the most abundant mineral group in Earth's crust. More than 4,000 minerals have been named, and several new ones are identified each year. Fortunately for students who are beginning to study minerals, no more than a few dozen are abundant. Collectively, these few make up most of the rocks of Earth's crust and, as such, they are often referred to as the rock-forming minerals. Although less abundant, many other minerals are used extensively in the manufacture of products and are called economic minerals. However, rock-forming minerals and economic minerals are not mutually exclusive groups. When found in large deposits, some rock-forming minerals are economically significant. One example is calcite, the primary component of the sedimentary rock limestone. Calcite has many uses, including the production of concrete. Classifying minerals. Minerals are placed into categories in much the same way that plants and animals are classified. Mineralogists use the term mineral species for a collection of specimens that exhibit similar internal structures and chemical compositions. Some common mineral species are quartz, calcite, galena, and pyrite. However, just as individual plants and animals within a species differ somewhat from one another, so do most specimens of the same mineral. Some mineral species are further subdivided into mineral varieties. For example, pure quartz is colorless and transparent. However, when small amounts of aluminum are incorporated into its atomic structure, quartz appears quite dark, in a variety called smoky quartz. Amethyst, another variety of quartz, owes its violet color to the presence of trace amounts of iron. Mineral species are assigned to mineral groups. Some important mineral groups are the silicates, carbonates, halides, and sulfates. Minerals within each class tend to have similar internal structures and, hence, similar properties. For example, minerals belonging to the carbonate group react chemically with acid, albeit to varying degrees, and many exhibit similar cleavage. Furthermore, minerals within the same group are often found together in the same rock. For example, halite and sylvite belong to the halide class and commonly occur together in evaporite deposits. Silicate versus non-silicate minerals. It is worth noting that only 8 elements make up the vast majority of the rock-forming minerals and represent more than 98% of Earth's continental crust. These elements, in order of most to least abundant, are oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. As shown in Figure 3.22, silicon and oxygen are by far the most common elements in Earth's crust. Furthermore, these two elements readily combine to form the basic building block for the most common mineral group, the silicates. More than 800 silicate minerals are known, and they account for about 92% of Earth's crust. The numbers represent percentages by weight. Figure 3.22 The 8 most abundant elements in the continental crust. Figure 3.22 Full alternative text description. Because other mineral groups are far less abundant in Earth's crust than the silicates, they are often grouped together under the heading non-silicates. Although these minerals are not as common as silicates, some non-silicates are very important economically. They provide us with iron and aluminum to build automobiles, gypsum for plaster and drywall for home construction, and copper wire that carries electricity and connects us to the internet. Common non-silicate mineral groups include the carbonates, sulfates, and halides. In addition to their economic importance, these groups include minerals that are major constituents in sediments and sedimentary rocks. Concept checks 3.5. 1. Distinguish between rock-forming minerals and economic minerals. 2. List the 8 most common elements in Earth's crust. 3. Distinguish between a mineral species and a variety. 3.6 The silicates. Sketch the silicon-oxygen tetrahedron and explain how this fundamental building block joins together to form various silicate structures. Every silicate mineral contains the 2 most abundant elements in Earth's crust, oxygen and silicon. Further, most contain one or more of the other common elements. Together, these elements give rise to hundreds of silicate minerals with a wide variety of properties, including hard quartz, soft talc, sheet-like mica, fibrous asbestos, green olivine, and blood-red garnet. Silicate structures. All silicate minerals have the same fundamental building block, the silicon-oxygen tetrahedron. This structure consists of 4 oxygen ions that are covalently bonded to one comparatively small silicon ion, forming a tetrahedron, a pyramid shape with 4 identical planar surfaces, or faces. These tetrahedrons are not chemical compounds but rather complex ions having a net charge of -4. To become electrically balanced, these complex ions bond to positively charged metal ions. Specifically, each O2 has one of its valence electrons bonding with the C4+ located at the center of the tetrahedron. The remaining negative charge on each oxygen is available to bond with another positive ion or with the silicon ion in an adjacent tetrahedron. Figure 3.23 2 representations of the silicon-oxygen tetrahedron. Minerals with independent tetrahedrons. One of the simplest silicate structures consists of independent tetrahedrons that have their 4 oxygen ions bonded to positive ions, such as Mg2+, Fe2+, and Ca2+. The mineral olivine, with the formula 2CO4, is a good example. In olivine, magnesium and or iron ions pack between comparatively large independent CO4 tetrahedrons, forming a dense, 3-dimensional structure. Garnet, another common silicate, is also composed of independent tetrahedrons ionically bonded to positive ions. Both olivine and garnet form dense, hard, equidimensional crystals that lack cleavage. Minerals with chain or sheet structures. One reason for the great variety of silicate minerals is the ability of CO4 tetrahedrons to link to one another in a variety of configurations. This important phenomenon, called polymerization, is achieved by the sharing of 1, 2, 3, or all 4 of the oxygen atoms with adjacent tetrahedrons. Vast numbers of tetrahedrons join together to form single chains, double chains, sheet structures, or 3-dimensional frameworks, as shown in Figure 3.24. Smart Figure 3.245 Basic silicate structures. Smart Figure 3.24 Full alternative text description. To see how oxygen atoms are shared between adjacent tetrahedrons, select one of the silicon ions near the middle of the single chain shown in Figure 3.24b. Notice that this silicon ion is completely surrounded by 4 larger oxygen ions. Also notice that 2 of the 4 oxygen atoms are bonded to 2 silicon atoms, whereas the other 2 are not shared in this manner. It is the linkage across the shared oxygen ions that joins the tetrahedrons into a chain structure. Now examine a silicon ion near the middle of the sheet structure and count the number of shared and unshared oxygen ions surrounding it. As you likely observed, the sheet structure is the result of 3 of the 4 oxygen atoms being shared by adjacent tetrahedrons. Watch tutorial, Silicate minerals. Minerals with 3-dimensional frameworks. In the most common silicate structure, all 4 oxygen ions are shared, producing a complex 3-dimensional framework. Quartz and the most common mineral group, the feldspars, exhibit this type of structure. The ratio of oxygen ions to silicon ions differs in each type of silicate structure. In independent tetrahedrons there are 4 oxygen ions for every silicon ion. In single chains, the oxygen to silicon ratio is 3:1. And in 3-dimensional frameworks, as found in quartz, the ratio is 2:1. As more oxygen ions are shared, the percentage of silicon in the structure increases. Silicate minerals are therefore described as having a low or high silicon content, based on their ratio of oxygen to silicon. Silicate minerals with 3-dimensional structures have the highest silicon content, while those composed of independent tetrahedrons have the lowest. Joining silicate structures. Except for quartz, the basic structure of most silicate minerals has a net negative charge. Therefore, metal ions are required to bring the overall charge into balance and to serve as the mortar that holds these structures together. The positive ions that most often link silicate structures are iron, magnesium, potassium, sodium, aluminum, and calcium. These positively charged ions bond with the unshared oxygen ions that occupy the corners of the silicate tetrahedrons. As a general rule, the covalent bonds between silicon and oxygen are stronger than the ionic bonds that hold one silicate structure to the next. Consequently, properties such as cleavage and, to some extent, hardness are controlled by the nature of the silicate framework. Quartz, which has only silicon-oxygen bonds, has great hardness and lacks cleavage, mainly because it has equally strong bonds in all directions. By contrast, the mineral talc has a sheet structure. Magnesium ions occur between the sheets and weakly join them together. The slippery feel of talcum powder is due to the silicate sheets sliding relative to one another, in much the same way that sheets of carbon atoms in graphite slide, giving graphite its lubricating properties. Recall that atoms of similar size can substitute freely for one another without altering a mineral's structure. For example, in olivine, iron and magnesium substitute for each other. This also holds true for the third most common element in Earth's crust, aluminum, which often substitutes for silicon in the center of silicon-oxygen tetrahedrons. Because most silicate structures will readily accommodate 2 or more different positive ions at a given bonding site, individual specimens of a particular mineral may contain varying amounts of certain elements. As a result, many silicate minerals form mineral groups that exhibit a range of compositions between 2 end members. Examples include the olivines, pyroxenes, amphiboles, micas, and feldspars. Concept checks 3.6. 1. Sketch the silicon-oxygen tetrahedron and label its parts. 2. What is the ratio of oxygen to silicon found in single tetrahedrons? How about framework structures? Which has the highest silicon content? 3. What differences in their silicate structures account for the slipperiness of talc and the hardness of quartz? 3.7 Common silicate minerals. Compare and contrast the light silicates with the dark silicates and list 3 common minerals in each group. The major groups of silicate minerals and common examples are given in Figure 3.25. Most silicate minerals, including those shown in Figure 3.25, form when molten rock cools and crystallizes. Cooling can occur at or near Earth's surface or at great depths. The environment during crystallization and the chemical composition of the molten rock determine, to a large degree, which minerals are produced. For example, the silicate mineral olivine crystallizes early, whereas quartz forms much later in the crystallization process. Figure 3.25 Common silicate minerals. Note that the complexity of the silicate structure increases from the top of the chart to the bottom. Figure 3.25 Full alternative text description. In addition to silicate minerals that crystallize from molten rock, some form at Earth's surface from other silicate minerals through the process of weathering. Still others are formed under the extreme pressures associated with mountain building. Each silicate mineral, therefore, has a structure and a chemical composition that indicate the conditions under which it formed. By carefully examining the mineral constituents of rocks, geologists can usually determine the circumstances under which the rocks formed. We will now examine some of the most common silicate minerals, which we divide into two major groups on the basis of their chemical makeup, the light silicates and the dark silicates. The light silicates. The light silicates are generally light in color and have a specific gravity of about 2.7, less than that of the dark silicates. These differences are mainly attributable to the presence or absence of iron and magnesium, which are heavy elements. The light silicates contain varying amounts of aluminum, potassium, calcium, and sodium rather than iron and magnesium. Feldspar group. Feldspar minerals are by far the most plentiful silicate group in Earth's crust, comprising about 51% of the crust. Their abundance can be partially explained by the fact that they can form under a wide range of temperatures and pressures. Two different feldspar structures exist. One group of feldspar minerals contains potassium ions in its structure and is therefore termed potassium feldspar. The other group, called plagioclase feldspar, contains both sodium and calcium ions that freely substitute for one another, depending on the environment during crystallization. Despite these differences, all feldspar minerals have similar physical properties. They have two planes of cleavage meeting at or near 90-degree angles, are relatively hard, and have a luster that ranges from glassy to pearly. As a component in igneous rocks, feldspar crystals can be identified by their rectangular shape and rather smooth, shiny faces. Also, note from this graph that the silicate minerals make up about 92% of Earth's crust. Figure 3.26 Feldspar minerals make up about 51% of Earth's crust. Figure 3.26 Full alternative text description. A. Characteristic crystal form of potassium feldspar. B. Most salmon-colored feldspar belongs to the potassium feldspar subgroup. C. Sodium-rich plagioclase feldspar tends to be light in color with a pearly luster. D. Calcium-rich plagioclase feldspar tends to be gray, blue-gray, or black in color. Labradorite, the sample shown here, exhibits striations on one of its crystal faces. Figure 3.27 Some common feldspar minerals. Figure 3.27 Full alternative text description. Potassium feldspar is usually light cream, salmon pink, or occasionally blue-green in color. The plagioclase feldspars, on the other hand, range in color from gray to blue-gray or sometimes black. However, color should not be used to distinguish these groups, as the only way to distinguish the feldspars by looking at them is through the presence of a multitude of fine parallel lines, called striations. Striations are found on some cleavage planes of plagioclase feldspar but are not present on potassium feldspar. Quartz. Quartz is the second most abundant mineral in the continental crust and the only common silicate mineral that consists entirely of silicon and oxygen. Because quartz contains a ratio of 2 oxygen ions for every silicon ion, no other positive ions are needed to attain neutrality. Thus, the term silica is commonly applied to quartz. In quartz, a three-dimensional framework is developed through the complete sharing of oxygen by adjacent silicon atoms. Thus, all the bonds in quartz are of the strong silicon, oxygen type. Consequently, quartz is hard, resists weathering, and does not have cleavage. When broken, quartz generally exhibits conchoidal fracture. When pure, quartz is clear and, if allowed to grow without interference, will develop hexagonal crystals that develop pyramid-shaped ends. However, like most other clear minerals, quartz is often colored by inclusions of various ions and often forms without developing good crystal faces. The most common varieties of quartz are milky, smoky, rose, amethyst, citron, and rock crystal. A smoky quartz is commonly found in coarse-grained igneous rocks. B. Rose quartz owes its color to small amounts of titanium. C. Milky quartz often occurs in veins, which occasionally contain gold. D. Amethyst, a purple variety of quartz. Figure 3.28 Quartz, the second most common mineral in Earth's crust, has many varieties. Muscovite. Muscovite is a common member of the mica family. It is light in color and has a pearly luster. Like other micas, muscovite has excellent cleavage in one direction. In thin sheets, muscovite is clear, a property that accounts for its use as window glass during the Middle Ages. Because muscovite is very shiny, it can often be identified by the sparkle it gives a rock. If you have ever looked closely at beach sand, you may have seen the glimmering brilliance of the mica flakes scattered among the other sand grains. Clay minerals. Clay is a term used to describe a category of complex minerals that, like the micas, have a sheet structure. Unlike other common silicates, most clay minerals originate as products of the chemical breakdown of other silicate minerals. Thus, clay minerals make up a large percentage of the surface material we call soil. Because of soil's importance to agriculture, and because of its role as a supporting material for buildings, clay minerals are extremely important to humans. In addition, clays account for nearly half the volume of sedimentary rocks. Clay minerals are generally very fine-grained, which makes them difficult to identify unless they are studied microscopically. Their layered structure and the weak bonding between layers give them a characteristic feel when wet. Clays are common in shales, mudstones, and other sedimentary rocks. One of the most common clay minerals is kaolinite, which is used in the manufacture of fine china and as a coating for high-gloss paper, such as that used in this textbook. Further, some clay minerals absorb large amounts of water, which allows them to swell to several times their normal size. These clays have been used commercially in a variety of ingenious ways, including as an additive to thicken milkshakes in fast food restaurants. Kaolinite is a common clay mineral formed by weathering of feldspar minerals. Figure 3.29 Kaolinite. The dark silicates. The dark silicates are minerals containing ions of iron and/or magnesium in their structure. Because of their iron content, ferromagnesian silicates are dark in color and have a greater specific gravity, between 3.2 and 3.6, than non-ferromagnesian silicates. The most common dark silicate minerals are olivine, the pyroxenes, the amphiboles, dark mica, and garnet. Olivine group. Olivine, a family of high-temperature silicate minerals, are black to olive green in color and have a glassy luster and a conchoidal fracture. Transparent olivine is occasionally used as a gemstone called peridot. Rather than developing large crystals, olivine commonly forms small, rounded crystals that give olivine-rich rocks a granular appearance. Olivine and related forms are typically found in basalt, a common igneous rock of the oceanic crust in volcanic areas on the continents, and are thought to constitute up to 50% of Earth's upper mantle. Commonly black to olive green in color, olivine has a glassy luster and is often granular in appearance. Olivine is commonly found in the igneous rock. Basalt. Pyroxene group. Figure 3.30 Olivine. The pyroxenes are a group of diverse minerals that are important components of dark-colored igneous rocks. The most common member, augite, is a black, opaque mineral with two directions of cleavage that meet at nearly a 90-degree angle. Augite is one of the dominant minerals in basalt. These dark-colored silicate minerals are common constituents of a variety of igneous rocks. Amphibole group. Figure 3.31 Augite and hornblende. Hornblende is the most common member of a chemically complex group of minerals called amphiboles. Hornblende is usually dark green to black in color, and except for its cleavage angles, which are about 60 degrees and 120 degrees, it is very similar in appearance to augite. In a rock, hornblende often forms elongated crystals. This helps distinguish it from pyroxene, which forms rather blocky crystals. Hornblende is found in igneous rocks, where it often makes up the dark portion of an otherwise light-colored rock. Biotite. Biotite is a dark, iron-rich member of the mica family. Like other micas, biotite possesses a sheet structure that gives it excellent cleavage in one direction. Biotite also has a shiny black appearance that helps distinguish it from the other dark ferromagnesian minerals. Like hornblende, biotite is a common constituent of igneous rocks, including the rock granite. Garnet. Garnet is similar to olivine in that its structure is composed of individual tetrahedrons linked by metallic ions. Also like olivine, garnet has a glassy luster, lacks cleavage, and exhibits conchoidal fracture. Although the colors of garnet are varied, this mineral is most often brown to deep red. Well-developed garnet crystals have 12 diamond-shaped faces and are most commonly found in metamorphic rocks. When transparent, garnets are prized as semi-precious gemstones. Garnets come in a variety of colors and are commonly found in mica-rich metamorphic rocks. Figure 3.32 Well-formed garnet crystal. Concept checks 3.7. 1. Apart from their difference in color, what is one main distinction between light and dark silicates? What accounts for this difference? 2. Based on the chart in Figure 3.25, what do muscovite and biotite have in common? How do they differ? 3. Is color a good way to distinguish between orthoclase and plagioclase feldspar? If not, what is a more effective means of distinguishing them? 3.8 Important non-silicate minerals. List the common non-silicate minerals and explain why each is important. Although the non-silicates make up only about 8% of Earth's crust, some non-silicate minerals, such as gypsum, calcite, and halite, occur as constituents in sedimentary rocks in significant amounts. Many non-silicates are also economically important. Non-silicate minerals are typically divided into groups based on the negatively charged ion or complex ion that the members have in common. For example, the oxides contain negative oxygen ions, which bond to one or more kinds of positive ions. Thus, within each mineral group, the basic structure and type of bonding is similar. As a result, the minerals in each group have similar physical properties that are useful in mineral identification. Figure 3.33 lists some of the major non-silicate mineral groups and includes a few examples of each. Figure 3.33 Full alternative text description. Figure 3.33 Important non-silicate mineral groups. Some of the most common non-silicate minerals belong to one of three groups of minerals: the carbonates, the sulfates, and the halides. The carbonate minerals are much simpler structurally than the silicates. This mineral group is composed of the carbonate ion and one or more kinds of positive ions. The two most common carbonate minerals are calcite, CaCO3, and dolomite, CaMg2. Calcite and dolomite are usually found together as the primary constituents in the sedimentary rocks limestone and dolostone. When calcite is the dominant mineral, the rock is called limestone, whereas dolostone results from a predominance of dolomite. Limestone is used in road aggregate and as a building stone, and it is the main ingredient in Portland cement. Did you know? Gypsum, a white to transparent mineral, was first used as a building material in Anatolia around 1600. It is also found on the interiors of the Great Pyramids in Egypt, which were erected in about 3700. Today, the average new American home contains more than 7 metric tons of gypsum in the form of 6,000 square feet of wallboard. Two other non-silicate minerals frequently found in sedimentary rocks are halite and gypsum. Both of these minerals are commonly found in thick layers that are the last vestiges of ancient seas that have long since evaporated. Like limestone, both halite and gypsum are important non-metallic resources. Halite is the mineral name for common table salt. Gypsum, which is calcium sulfate with water bound into the structure, is the mineral from which plaster and other similar building materials are composed. Halite mine in Grand Saline, Texas. Note the person for scale. Figure 3.34 thick bed of halite exposed in an underground mine. Most non-silicate mineral classes contain members that are prized for their economic value. This includes the oxides, whose members hematite and magnetite are important ores of iron. Also significant are the sulfides, which are basically compounds of sulfur and one or more metals. Important sulfide minerals include galena, sphalerite, and chalcopyrite. In addition, native elements, including gold, silver, and carbon, are economically important, as are a host of other non-silicate minerals, fluorite, corundum, and uranite. Concept checks 3.8. 1. Lists 6 common non-silicate mineral groups. What key ions or elements define each group? 2. What is the most common carbonate mineral? 3. List 8 common non-silicate minerals and their economic uses. 3.9 Minerals, a non-renewable resource. Discuss Earth's mineral resources in terms of renewability. Differentiate between mineral resources and/or deposits. Earth's crust and oceans are the source of a wide variety of useful and valuable materials. From the first use of clay to make pottery nearly 10,000 years ago, the use of earth materials has expanded, resulting in more complex societies and our modern civilization. The mineral and energy resources we extract from Earth's crust are the raw materials from which we make all the products we use. Natural resources are typically grouped into broad categories according to their ability to be regenerated or their origin or type. Here we will consider mineral resources. However, other natural resources are indispensable to humans, including air, water, and solar energy. Renewable versus non-renewable resources. Resources classified as renewable can be replenished over relatively short time spans. Common examples are corn used for food and for making ethanol, natural fibers such as cotton for clothing, and forest products for lumber and paper. Energy from flowing water, wind, and the sun are also considered renewable. The Ivanpah Solar Electric Generating System is a solar thermal plant located in California's Mojave Desert, southwest of Las Vegas. It consists of 173,500 heliostats, each with 2 mirrors that focus solar energy on boilers located on one of 3 centralized towers. The boilers, in turn, generate steam which turns turbines that generate electricity. Figure 3.35 Solar energy is renewable. By contrast, many other basic resources are classified as non-renewable. Important metals such as iron, aluminum, and copper fall into this category, as do our many widely used fuels, oil, natural gas, and coal. Although these and other resources form continuously, the processes that create them are so slow that significant deposits take millions of years to accumulate. Thus, for all practical purposes, Earth contains fixed quantities of these substances. The present supplies will be depleted as they are mined or pumped from the ground. Although some non-renewable resources, such as the aluminum we use for containers, can be recycled, others, such as the oil burned for fuel, cannot. Did you know? One of the world's heaviest cut and polished gemstones is a 22,892.5 carat golden yellow topaz. Currently housed in the Smithsonian Institution, this roughly 10-pound gem is about the size of an automobile headlight and could hardly be used as a piece of jewelry, except perhaps by an elephant. Mineral resources and/or deposits. Today, practically every manufactured product contains materials obtained from minerals. Figure 3.33 lists some of the most economically important mineral groups. Mineral resources are occurrences of useful minerals that are formed in such quantities that eventual extraction is reasonably certain. Mineral resources include deposits of metallic minerals that can be presently extracted profitably, as well as known deposits that are not yet economically or technologically recoverable. Materials used for such purposes as building stone, road aggregate, abrasives, ceramics, and fertilizers are not usually called mineral resources, rather, they are classified as industrial rocks and minerals. An ore deposit is a naturally occurring concentration of one or more metallic minerals that can be extracted economically. In common usage, the term ore is also applied to some non-metallic minerals such as fluorite and sulfur. Recall that more than 98% of Earth's crust is composed of only 8 elements, and except for oxygen and silicon, all other elements make up a relatively small fraction of common crustal rocks. Indeed, the natural concentrations of many elements are exceedingly small. A deposit containing the average concentration of an element such as gold has no economic value because the cost of extracting it greatly exceeds the value of the gold that could be recovered. Did you know? The names of precious gems often differ from the names of parent minerals. For example, sapphire is one of 2 gems that are varieties of the same mineral, corundum. Tiny amounts of the elements titanium and iron in corundum produce the most prized blue sapphires. When the mineral corundum contains chromium, it exhibits a brilliant red color, and the gem is called ruby. In order to have economic value, an ore deposit must be highly concentrated. For example, copper makes up about 0.0068% of the crust. For a deposit to be considered a copper ore, it must contain a concentration of copper that is about 100 times this amount, or about 0.68%. Aluminum, on the other hand, represents about 8.1% of the crust and can be extracted profitably when it is found in concentrations 3 or 4 times that amount. It is important to understand that due to economic or technological changes, a deposit may either become profitable to extract or lose its profitability. If the demand for a metal increases and its value rises sufficiently, the status of a previously unprofitable deposit can be upgraded from a mineral to an ore. Technological advances that allow a resource to be extracted more efficiently and, thus, more profitably than before may also trigger a change of status. Conversely, changing economic factors can turn what was once a profitable ore deposit into an unprofitable mineral deposit. This situation was illustrated at the copper mining operation located at Bingham Canyon, Utah, one of the largest open-pit mines on Earth. Mining was halted there in 1985 because outmoded equipment had driven the cost of extracting the copper beyond the current selling price. In 1989, new owners responded by replacing an antiquated 1,000-car railroad with more modern conveyor belts and dump trucks for efficiently transporting the ore and waste. The advanced equipment reduced extraction costs by nearly 30%, ultimately returning the copper mine operation to profitability. Today, the Bingham Canyon mine produces nearly 25% of the refined copper in the United States. In addition to producing 300,000 metric tons of copper, the Bingham Canyon mine produces about 400,000 ounces of gold, 4 million ounces of silver, and 25 million pounds of molybdenum. Although the amount of copper in the rock is less than 0.5%, the huge volume of material removed and processed each day yields enough metal to be profitable. In addition to copper, this mine produces gold, silver, and molybdenum. Figure 3.36 Aerial view of Bingham Canyon Copper Mine near Salt Lake City, Utah. Over the years, geologists have been keenly interested in learning how natural processes produce localized concentrations of essential minerals. One well-established fact is that occurrences of valuable mineral resources are closely related to the rock cycle. That is, the mechanisms that generate igneous, sedimentary, and metamorphic rocks, including the processes of weathering and erosion, play a major role in producing concentrated accumulations of useful elements. Moreover, with the development of the theory of plate tectonics, geologists have added another tool for understanding the processes by which one rock is transformed into another. As these rock-forming processes are examined in the following chapters, we consider their role in producing some of our important mineral resources. Concept checks 3.9. 1. List 3 examples of renewable resources and 3 examples of non-renewable resources. 2. Compare and contrast a mineral resource and an ore deposit. 3. Explain how a mineral deposit that previously could not be mined profitably might be upgraded to an ore deposit. Concepts in review: matter and minerals. 3.1 Minerals, building blocks of rocks. List the main characteristics that an earth material must possess to be considered a mineral and describe each characteristic. Key terms. Mineralogy: mineral rock. In earth science, the word mineral refers to naturally occurring inorganic solids that possess an orderly crystalline structure and a characteristic chemical composition. The study of minerals is called mineralogy. Minerals are the building blocks of rocks. Rocks are naturally occurring masses of minerals or mineral-like matter such as natural glass or organic material. 3.2 Atoms, building blocks of minerals. Compare and contrast the 3 primary particles contained in atoms. Key terms. Atom: nucleus, proton, neutron, electron, valence, electron, atomic number, element, periodic table, chemical compound. Minerals are composed of atoms of one or more elements. All atoms consist of the same 3 basic components: protons, neutrons, and electrons. The atomic number represents the number of protons found in the nucleus of an atom of a particular element. For example, an oxygen atom has 8 protons, so its atomic number is 8. Protons and neutrons have approximately the same size and mass, but protons are positively charged, whereas neutrons have no charge. Electrons weigh only about 1/2000 as much as protons or neutrons. They occupy the space around the nucleus, where they form what can be thought of as a cloud that is structured into several distinct energy levels called principal shells. The electrons in the outermost principal shell, called valence electrons, are responsible for the bonds that hold atoms together to form chemical compounds. Elements that have the same number of valence electrons tend to behave similarly. The periodic table is organized so that elements with the same number of valence electrons form a column, called a group. Use the periodic table to identify the geologically important elements that have the following numbers of protons: 14, 6, 13, 17, and 26. 3.3 Why atoms bond. Distinguish among ionic bonds, covalent bonds, and metallic bonds. Key terms. Octet rule: chemical bond, ionic bond, ion. Covalent bond, metallic bond. When atoms are attracted to other atoms, they can form chemical bonds, which generally involve the transfer or sharing of valence electrons. The most stable arrangement for most atoms is to have 8 electrons in the outermost principal shell. This concept is called the octet rule. To form ionic bonds, atoms of one element give up one or more valence electrons to atoms of another element, forming positively and negatively charged atoms called ions. The ionic bond results from the attraction between oppositely charged ions. Covalent bonds form when adjacent atoms share valence electrons. In metallic bonds, the sharing is more extensive. The shared valence electrons can move freely through the substance. Which of the accompanying diagrams best illustrates ionic bonding? What are the distinguishing characteristics of ionic versus covalent bonding? 3.4 Properties of minerals. List and describe the properties used in mineral identification. Key terms. Diagnostic property, ambiguous property, luster, color, streak, crystal shape, habit, hardness. Mohs scale, cleavage, fracture, tenacity, density, specific gravity. The composition and internal crystalline structure of a mineral give it specific physical properties. Mineral properties useful in identifying minerals are termed diagnostic properties. Luster is a mineral's ability to reflect light. The terms transparent, translucent, and opaque describe the degree to which a mineral can transmit light. Color can be unreliable for mineral identification, as impurities can stain minerals with diverse colors. A more reliable identifier is streak, the color of the powder generated by scraping a mineral against a porcelain streak plate. Crystal shape, also called crystal habit, is often useful for mineral identification. Variations in the strength of chemical bonds give minerals properties such as hardness and tenacity. Cleavage, the preferential breakage of a mineral along planes of weakly bonded atoms, is very useful in identifying minerals. The amount of matter packed into a given volume determines a mineral's density. To compare the densities of minerals, mineralogists use a related quantity, known as specific gravity, which is the ratio between a mineral's density and the density of water. Other properties are diagnostic for certain minerals but rare in most others. Examples include smell, taste, feel, reaction to hydrochloric acid, magnetism, and double refraction. Research the minerals quartz and calcite. List 5 physical characteristics that may be used to distinguish one from the other. 3.5 Mineral groups. Explain how minerals are classified and name the most abundant mineral group in Earth's crust. Key terms. Rock-forming mineral, economic mineral, silicate, non-silicate. More than 4,000 different minerals have been identified, but only a few dozen are common in Earth's crust. These are the rock-forming minerals. Many minerals have economic value. Minerals are placed into classes on the basis of similar crystal structures and compositions. Minerals of the same class tend to have similar properties and are found in similar geologic settings. Silicon and oxygen are the most common elements in Earth's crust, and so the most common minerals in the crust are silicate minerals. In comparison, non-silicate minerals make up only about 8% of the crust. 3.6 The silicates. Sketch the silicon, oxygen tetrahedron and explain how this fundamental building block joins together to form various silicate structures. Key terms. Silicon, oxygen tetrahedron. Polymerization. Silicate minerals have a basic building block in common, a small pyramid-shaped structure consisting of one silicon atom surrounded by 4 oxygen atoms. Because this structure has 4 sides, it is called the silicon-oxygen tetrahedron. Individual tetrahedrons can be bonded to other elements, such as aluminum, iron, or potassium. Neighboring tetrahedrons can share some of their oxygen atoms, causing them to develop long chains. This is the process of polymerization. Polymerization can produce silicate mineral structures with high or low degrees of oxygen sharing. The more sharing there is, the higher the ratio of silicon to oxygen. polymerization can produce unit cells that are single chains of tetrahedrons, double chains, sheets of shared tetrahedrons, or even complicated three-dimensional networks of tetrahedrons that share all the oxygen atoms in the mineral. 3.7 Common silicate minerals. Compare and contrast the light silicates with the dark silicates and list 3 common minerals in each group. Key terms. Light silicate. Non-ferromagnesian silicate. Potassium feldspar plagioclase feldspar quartz muscovite clay dark silicate. Ferromagnesian silicate olivine augite hornblende biotite garnet. Silicate minerals are the most common mineral class on Earth. They are subdivided into minerals that contain iron and/or magnesium and those that do not. Non-ferromagnesian silicates are generally light in color and generally of relatively low specific gravity. Feldspar, quartz, muscovite, and clays are all examples. Ferromagnesian silicates are generally dark in color and relatively dense. Olivine, pyroxene, amphibole, biotite, and garnet are all examples. In general, non-ferromagnesian silicates are light in color, shades of peach, tan, clear, or white. What could account for the fact that some non-ferromagnesian silicates are dark-colored, like the smoky quartz in this photo? 3.8 Important non-silicate minerals. List the common non-silicate minerals and explain why each is important. Key terms. Calcite. Dolomite, halite, gypsum. Non-silicate mineral groups don't include the silicon-oxygen tetrahedron. Instead, these minerals use other negatively charged ions or complex ions. Non-silicate minerals are grouped on the basis of their negatively charged ion or ion complex. Common groups are the oxides, carbonates, sulfates, and halides. Non-silicate minerals are often economic minerals. Hematite is an important source of industrial iron, while calcite is a critical component of cement. Halite makes popcorn taste good. 3.9 Minerals, a non-renewable resource. Discuss Earth's mineral resources in terms of renewability. Differentiate between mineral resources and/or deposits. Key terms. Renewable, non-renewable mineral resource or deposit. Resources are classified as renewable when they can be replenished over short time spans and non-renewable when they can't. Ore deposits are naturally occurring concentrations of one or more metallic minerals that can be extracted economically using current technology. A mineral resource can be upgraded to an ore deposit if the price of the commodity increases sufficiently or if the cost of extraction decreases. The reverse can also happen. Give it some thought. 1. Using the geologic definition of mineral as your guide, determine which of the items in this list are minerals and which are not. If something in this list is not a mineral, explain. A. Gold nugget. B. Seawater. C. Quartz. D. Cubic zirconia. E. Obsidian. F. Ruby. G. Glacial ice. H. Amber. 2. Assume that the number of protons in a neutral atom is 92 and the atomic mass is 238.03. What is the name of the element? B. How many electrons does it have? 3. Referring to the accompanying photos of 5 minerals, determine which of these specimens exhibit a metallic luster and which have a non-metallic luster. 4. Gold has a specific gravity of almost 20. A 5-gallon bucket of water weighs 40 pounds. How much would a 5-gallon bucket of gold weigh? 5. Examine the accompanying photo of a mineral that has several smooth, flat surfaces that resulted when the specimen was broken. A. How many flat surfaces are present on this specimen? B. How many different directions of cleavage does this specimen have? C. Do the cleavage directions meet at 90-degree angles? 6. Each of the following statements describes a silicate mineral or mineral group. In each case, provide the appropriate name A, the most common member of the amphibole group B, the most common light-colored member of the mica family C, the only common silicate mineral made entirely of silicon and oxygen, D, a silicate mineral with a name based on its color E, a silicate mineral characterized by striations, F, silicate minerals that originate as a product of chemical weathering. 7. What mineral property is illustrated in the accompanying photo? 8. Do an internet search to determine which minerals are used to manufacture the following products. A. Stainless steel utensils. B. Cat litter. C. Tums brand antacid tablets. D. Lithium batteries. E. Aluminum beverage cans. 9. Examine figure 3.33. What would be the most abundant elements on a planet composed of mostly halide minerals instead of silicate minerals? What about a carbonate planet? 10. The accompanying diagram shows one of several possible ways that silicon-oxygen tetrahedrons can bond together. Describe the silica structure shown and name a mineral group that displays this type of silicate structure. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, and the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 4: Igneous Rocks and Intrusive Activity. Granite outcrops reflected in Tenaya Lake, Yosemite National Park, California. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 4.1 list and describe the three major components of magma. 4.2 Compare and contrast the four basic igneous compositions, felsic, intermediate, mafic, and ultramafic. 4.3 Identify and describe the six major igneous textures. 4.4 Distinguish among the common igneous rocks based on texture and mineral composition. 4.5 Summarize the major processes that generate magma from solid rock. 4.6 Describe how magmatic differentiation can generate a magma body that has a mineralogy that is different from its parent magma. 4.7 Describe how partial melting of the mantle rock peridotite can generate a basaltic magma. 4.8 Compare and contrast these intrusive igneous structures, dikes, sills, batholiths, stocks, and laccoliths. 4.9 Explain how economic deposits of gold, silver, and many other metals form. Understanding the structure, composition, and internal workings of our planet requires a basic knowledge of igneous rocks. Igneous rocks and metamorphic rocks derived from igneous parents make up most of Earth's crust and mantle. Thus, Earth can be described as a huge mass of igneous and metamorphic rocks that is covered with a thin veneer of sedimentary rock and has a relatively small iron-rich core. Many prominent landforms are composed of igneous rocks, including volcanoes such as Mount Rainier and the large igneous bodies that make up the Sierra Nevada, the Black Hills, and the high peaks of the Adirondacks. Igneous rocks also make excellent building stones and are widely used as decorative materials, such as for monuments and household countertops. 4.1 Magma, parent material of igneous rock. List and describe the three major components of magma. Our discussion of the rock cycle in Chapter 1 explained that igneous rocks form as molten rock cools and solidifies. Considerable evidence supports the idea that the parent material for igneous rocks, called magma, is formed by partial melting that occurs at various levels within Earth's crust and upper mantle to depths of about 250 kilometers. Once formed, a magma body buoyantly rises toward the surface because it is less dense than the surrounding rocks. Occasionally, molten rock reaches Earth's surface, where it is called lava, figure 4. 1. Sometimes lava is emitted as fountains that are produced when escaping gases propel it from a magma chamber. On other occasions, lava is explosively ejected, producing dramatic eruptions of steam and volcanic ash. However, not all eruptions are violent. Many volcanoes emit quiet outpourings of fluid lava. The nature of magma. Magma is rock that is completely or partly molten, and when cooled it solidifies to form igneous rocks mainly composed of silicate minerals. Most magmas consist of three materials: a liquid component, a solid component, and a gaseous component. Figure 4.1 Eruption of Mount Etna, July 2014, Sicily, Italy. The liquid portion, called melt, is composed mainly of mobile ions of the 8 most common elements found in Earth's crust: silicon and oxygen, along with lesser amounts of aluminum, potassium, calcium, sodium, iron, and magnesium. The solid components in magma are crystals of silicate minerals. As a magma body cools, the size and number of crystals increase. During the last stage of cooling, a magma body is like a crystalline mush that contains only small amounts of melt. The gaseous components of magma, called volatiles, are materials that vaporize at surface pressures. The most common volatiles found in magma are water vapor, carbon dioxide, and sulfur dioxide. When magma is deep below the surface, the immense confining pressure keeps these volatiles dissolved in the melt, the way carbon dioxide is dissolved in soda before you open the can. As the melt rises toward the surface and the confining pressure is reduced, the volatiles begin to separate from the melt, again, similar to the way carbon dioxide forms bubbles when you reduce the pressure in a soda can by opening it. As the gases build up, they may eventually propel magma from the vent. When deeply buried magma bodies crystallize, the remaining volatiles collect as hot, water-rich fluids that migrate through openings in the surrounding rocks. These hot fluids play an important role in metamorphism and will be considered in Chapter 8. From magma to crystalline rock. To better understand how magma crystallizes, let us first consider how a simple crystalline solid melts. Recall that, in any crystalline solid, the ions are arranged in a closely packed regular pattern. However, they are not without some motion. They exhibit a restricted vibration about fixed points. As the temperature rises, ions vibrate more rapidly and consequently collide with ever-increasing vigor with their neighbors. Thus, heating causes the ions to occupy more space, which in turn causes the solid to expand. When the ions are vibrating rapidly enough to overcome the force of their chemical bonds, melting occurs. At this stage, the ions are able to slide past one another, and the orderly crystalline structure disintegrates. Thus, melting converts a solid consisting of tight, uniformly packed ions into a liquid composed of unordered ions moving randomly about. In the process called crystallization, cooling reverses the events of melting. As the temperature of the liquid drops, ions pack more closely together as their rate of movement slows. When they are cooled sufficiently, the forces of the chemical bonds again confine the ions to an orderly crystalline arrangement. When a magma body cools, the silicon and oxygen atoms link together first to form silicon-oxygen tetrahedra, the basic building blocks of the silicate minerals. As magma continues to lose heat to its surroundings, the tetrahedra join with each other and with other ions to form embryonic crystal nuclei. Each nucleus slowly grows as ions lose their mobility and join the crystalline network. The minerals that form the earliest have space to grow and tend to have better developed crystal faces than do the ones that form later and occupy the remaining spaces. Eventually, all of the melt is transformed into a solid mass of interlocking silicate minerals that we call an igneous rock. The largest crystals are about 1 centimeter in length. Igneous processes. Figure 4.2 Igneous rock composed of interlocking crystals. Igneous rocks form in two basic settings. Molten rock may crystallize within Earth's crust over a range of depths, or it may solidify at Earth's surface. Smart Figure 4.3 Full Alternative Text Description. Smart Figure 4.3 Intrusive versus Extrusive Igneous Rocks. Watch tutorial, Intrusive versus Extrusive. When magma crystallizes at depth, it forms intrusive igneous rocks, also known as plutonic rocks, after Pluto, the god of the underworld in classical mythology. These rocks can be observed at the surface in locations where uplifting and erosion have stripped away the overlying rocks. Exposures of intrusive igneous rocks occur in many places, including the White Mountains, New Hampshire, Stone Mountain in Georgia, Mount Rushmore in the Black Hills of South Dakota, and Yosemite National Park, California. This memorial, located in the Black Hills of South Dakota, is carved from intrusive igneous rocks. Figure 4.4 Mount Rushmore National Memorial. Igneous rocks that form when molten rock solidifies at the surface are classified as extrusive igneous rocks. They are also called volcanic rocks, after Vulcan, the Roman fire god. Extrusive igneous rocks form when lava solidifies or when volcanic debris falls to Earth's surface. Extrusive igneous rocks are abundant in western portions of the Americas, where they make up the volcanic peaks of the Cascade Range and the Andes Mountains. In addition, many oceanic islands, including the Hawaiian chain and Alaska's Aleutian Islands, are composed almost entirely of extrusive igneous rocks. The nature of volcanic activity will be addressed in more detail in Chapter 5. Concept Checks 4.1. 1. What is magma? How does magma differ from lava? 2. List and describe the three components of magma. 3. Describe the process of crystallization. 4. Compare and contrast extrusive and intrusive igneous rocks. 4.2 Igneous compositions. Compare and contrast the four basic igneous compositions: felsic, intermediate, mafic, and ultramafic. Igneous rocks are composed mainly of silicate minerals. Chemical analyses show that silicon and oxygen are by far the most abundant constituents of igneous rocks. These two elements, plus ions of aluminum, calcium, sodium, potassium, magnesium, and iron, make up roughly 98%, by weight, of most magmas. In addition, magma contains small amounts of many other elements, including titanium and manganese, and trace amounts of rare elements, such as gold, silver, and uranium. As magma cools and solidifies, these elements combine to form two major groups of silicate minerals. The dark silicates are rich in iron and or magnesium and comparatively low in silica. Olivine, pyroxene, amphibole, and biotite mica are the common dark silicate minerals of Earth's crust. By contrast, the light silicates contain greater amounts of potassium, sodium, and calcium. The light silicate minerals, including quartz, muscovite mica, and the most abundant mineral group, the feldspars, are richer in silica than the dark silicates. Compositional categories. Despite the great compositional diversity of igneous rocks, geologists classify these rocks into four broad groups according to their proportions of light and dark minerals. As shown in Figure 4.5, these compositional groups are felsic, intermediate, mafic, and ultramafic. Smart Figure 4.5 Mineral makeup of common igneous rocks. Smart Figure 4.5 Full alternative text description. Felsic versus mafic. Watch tutorial, Igneous composition. Near one end of the continuum are rocks composed almost entirely of light-colored silicates, quartz, and potassium feldspar. The composition of igneous rocks dominated by these minerals is classified as felsic, a term derived from feldspar and silica. Because felsic magmas most commonly solidify to form granite, geologists also refer to this type of magma as having a granitic composition. In addition to quartz and feldspar, most granitic rocks contain about 10% dark silicate minerals, usually biotite mica and amphibole. Other notable characteristics of felsic rocks and the magma from which they were derived is that they are rich in silica and are major constituents of the continental crust. Inset images are photomicrographs that show the interlocking crystals that make up granite and basalt, respectively. Figure 4.6 Granitic versus basaltic compositions. Figure 4.6 Full alternative text description. Rocks that contain at least 45% dark silicates are classified as mafic. As a result of their iron content, mafic rocks are typically darker and denser than felsic rocks. Because mafic magmas most often solidify to form the igneous rock basalt, geologists also refer to this type of magma as having a basaltic composition. Basaltic rocks make up the ocean floor as well as many of the volcanic islands located within the ocean basins. Basalt also forms extensive lava flows on the continents. Other compositional groups. As illustrated in Figure 4.5, rocks with a composition between felsic and mafic rocks are said to have an intermediate or andesitic composition after the common volcanic rock andesite. Intermediate rocks contain at least 25% dark silicate minerals, mainly amphibole, pyroxene, and biotite mica, with the other dominant mineral being plagioclase feldspar. This important category of igneous rocks is often associated with volcanic activity on the seaward margins of continents and on volcanic island arcs such as the Aleutian chain. Another important igneous rock, peridotite, contains mostly olivine and pyroxene and thus falls on the opposite side of the compositional spectrum from felsic rocks. Because peridotite is composed almost entirely of ferromagnesian minerals, its chemical composition is referred to as ultramafic. Although ultramafic rocks are rare at Earth's surface, peridotite is the main constituent of the upper mantle. Silica content as an indicator of composition. An important aspect of the chemical composition of igneous rocks is silica content. Typically, the silica content of crustal rocks ranges from as low as about 40% in ultramafic rocks to a high of more than 70% in felsic rocks. The percentage of silica in igneous rocks varies in a systematic manner that parallels the abundance of other elements. For example, rocks that are relatively low in silica contain large amounts of iron, magnesium, and calcium. By contrast, rocks that are high in silica contain comparatively less iron, magnesium, and calcium but are enriched with sodium and potassium. Consequently, the chemical makeup of an igneous rock can be inferred directly from its silica content. Further, the amount of silica present in magma strongly influences the magma's behavior. Felsic magma, which has a high silica content, is quite viscous and may erupt at temperatures as low as 650 degrees Celsius, whereas mafic magmas, which are low in silica, are generally more fluid. Mafic magmas also erupt at higher temperatures than felsic magmas, usually at temperatures between 1050 degrees and 1250 degrees Celsius. Did you know? The most abundant element in Earth's crust is oxygen. It makes up 47% of Earth's crust by weight and 94% by volume. In fact, oxygen atoms are so much bigger than most of the other atoms in common minerals that Earth's crust is mainly oxygen atoms packed closely together, with smaller atoms such as silicon, aluminum, and potassium tucked in between. Concept checks 4.2. 1. Igneous rocks are composed mainly of which group of minerals? 2. How do light-colored igneous rocks differ in composition from dark-colored igneous rocks? 3. List the 4 basic compositional groups of igneous rocks, in order from the group with the highest silica content to the group with the lowest silica content. 4. Name 2 minerals typically found in rocks with high silica content and 2 minerals found in rocks with relatively low silica content. For point 3 igneous textures, what can they tell us? Identify and describe the 6 major igneous textures. The term texture is used to describe the overall appearance of a rock based on the size, shape, and arrangement of its mineral grains, not how it feels to touch. Texture is an important property because it reveals a great deal about the environment in which the rock formed. Geologists can make inferences about a rock's origin based on careful observations of grain size and other characteristics of the rock. Smart Figure 4.7 Igneous Rock Textures. Smart Figure 4.7 Full Alternative Text Description. 3 factors influence the textures of igneous rocks. The rate at which the molten rock cools. The amount of silica in the magma. Watch tutorial, Igneous Textures. The amount of dissolved gases in the magma. Among these, the rate of cooling tends to be the dominant factor. A very large magma body located many kilometers beneath Earth's surface remains insulated from lower surface temperatures by the surrounding rock and thus cools very slowly over a period of perhaps tens of thousands to millions of years. Initially, a relatively small number of crystal nuclei form. This slow cooling permits ions to migrate freely until they eventually join one of the existing crystals. Consequently, slow cooling promotes the growth of fewer but larger crystals. On the other hand, when cooling occurs rapidly, for example, in a thin lava flow, the ions quickly lose their mobility and readily combine to form crystals. This results in the development of numerous embryonic crystal nuclei, all of which compete for the available ions. The result is a solid mass of many tiny intergrown crystals. Types of igneous textures. In addition to cooling quickly or slowly, a magma body may migrate to a new location or erupt at the surface before it completely solidifies. As a result, several types of igneous textures exist, including aphanitic, phaneritic, porphyritic, vesicular, glassy, and pyroclastic. Aphanitic texture. Igneous rocks that form at the surface or as small intrusive masses within the upper crust where cooling is relatively rapid exhibit a fine-grained texture termed aphanitic. By definition, the crystals that make up aphanitic rocks are so small that individual minerals can be distinguished only with the aid of a polarizing microscope or using sophisticated techniques. Therefore, we commonly characterize fine-grained rocks as being light, intermediate, or dark in color. Using this system, light-colored aphanitic rocks are those containing primarily light-colored non-ferromagnesian silicate minerals. Phaneritic texture. When large masses of magma slowly crystallize at great depth, they form igneous rocks that exhibit a coarse-grained texture described as phaneritic. Coarse-grained rocks consist of a mass of intergrown crystals that are roughly equal in size and large enough for the individual minerals to be distinguished without the aid of a microscope. Geologists often use a small magnifying lens to aid in identifying minerals in phaneritic rocks. Porphyritic texture. A large mass of magma may require thousands or even millions of years to solidify. Because different minerals crystallize under different environmental conditions, it is possible for crystals of one mineral to become quite large before others even begin to form. If molten rock containing some large crystals moves to a different environment, for example, by erupting at the surface, the remaining liquid portion of the lava cools more quickly. The resulting rock, which has large crystals embedded in a matrix of smaller crystals, is said to have a porphyritic texture. The large crystals in porphyritic rocks are termed phenocrysts, whereas the matrix of smaller crystals is called ground mass. A rock with a porphyritic texture is termed a porphyry. The large crystals in porphyritic rocks are called phenocrysts, and the matrix of smaller crystals is called ground mass. Figure 4.8 Porphyritic texture. Vesicular texture. Common features of many extrusive rocks are the voids left by gas bubbles that escape as lava solidifies. These nearly spherical openings are called vesicles, and the rocks that contain them are said to have a vesicular texture. Rocks that exhibit a vesicular texture often form in the upper zone of a lava flow, where cooling occurs rapidly enough to preserve the openings produced by the expanding gas bubbles. Another common vesicular rock, called pumice, forms when silica-rich lava is ejected during an explosive eruption. The larger image shows a lava flow on Hawaii's Kilauea volcano. The inset photo is a close-up showing the vesicular texture of hardened lava. Vesicles are small holes left by escaping gas bubbles. Figure 4.9 Vesicular texture. Glassy texture. During some volcanic eruptions, molten rock is ejected into the atmosphere, where it is quenched to become a solid. Rapid cooling of this type may generate rocks having a glassy texture. Glass results when unordered ions are frozen in place before they are able to unite into an orderly crystalline structure. Obsidian, a common type of natural glass, is similar in appearance to dark chunks of manufactured glass. Obsidian's excellent conchoidal fracture and ability to hold a sharp, hard edge made it a prized material from which Native Americans chipped arrowheads and cutting tools. Native Americans made arrowheads and cutting tools from obsidian, a natural glass. Figure 4.10 Obsidian arrowhead. Obsidian flows, typically a few hundred feet thick, provide evidence that rapid cooling is not the only mechanism that produces a glassy texture. Magmas with high silica content tend to form long, chain-like structures. Before crystallization is complete. These structures, in turn, slow the migration of ions, which impedes the formation of crystals. In addition, these long chain-like structures increase the magma's viscosity. So granitic magma, which is rich in silica, may be extruded as an extremely viscous mass that eventually solidifies to form obsidian. By contrast, basaltic magma, which is low in silica, forms very fluid lavas that, upon cooling, usually generate fine-grained crystalline rocks. However, when a basaltic lava flow enters the ocean, its surface is quenched rapidly enough to form a thin, glassy skin. Pyroclastic texture. Another group of igneous rocks is formed from the consolidation of individual rock fragments ejected during explosive volcanic eruptions. The ejected particles might be very fine volcanic ash, molten blobs, or large angular blocks torn from the walls of a vent during an eruption. Igneous rocks composed of these rock fragments are said to have a pyroclastic texture, or fragmental texture. This eruptive column consists in part of volcanic fragments, which will fall out and may eventually consolidate to become rocks displaying a pyroclastic texture. Figure 4.11 Pyroclastic rocks are the product of explosive eruptions. A common type of pyroclastic rock, called welded tuff, is composed of fine fragments of glass that remained hot enough to fuse together. Other pyroclastic rocks are composed of fragments that solidified before impact and became cemented together at some later time. Because pyroclastic rocks are made of individual particles or fragments rather than interlocking crystals, their textures often resemble those exhibited by sedimentary rocks rather than those associated with igneous rocks. Concept checks 4.3. 1. Define texture. 2. How does the rate of cooling influence crystal size? What other factors influence the texture of igneous rocks? 3. List the 6 major igneous rock textures. 4. What does a porphyritic texture indicate about the cooling history of an igneous rock? 4.4 Naming igneous rocks. Distinguish among the common igneous rocks based on texture and mineral composition. Geologists classify igneous rocks on the basis of their texture and mineral composition. The various igneous textures described in the previous section result mainly from different cooling histories, whereas the mineral composition of an igneous rock depends on the chemical makeup of its parent magma. Because igneous rocks are classified on the basis of both mineral composition and texture, some rocks having similar mineral constituents but exhibiting different textures are given different names. Igneous rocks are classified based on mineral composition and texture. Smart Figure 4.12 Classification of igneous rocks. Smart Figure 4.12 Full alternative text description. Watch tutorial, Classification of igneous rocks. Felsic igneous rocks. Granite. Of all the igneous rocks, granite is perhaps the best known. This is because of its natural beauty, which is enhanced when it is polished, and its abundance in the continental crust. Slabs of polished granite are commonly used for tombstones and monuments and as building stones. Well-known areas in the United States where granite is quarried include Barre, Vermont, Mount Airy, North Carolina, and St. Cloud, Minnesota. Granite is a coarse-grained rock composed of about 10 to 20% quartz and roughly 50% feldspar. When examined close up, the quartz grains appear somewhat rounded in shape, glassy, and clear to gray in color. By contrast, feldspar crystals, which are generally white, gray, or salmon pink in color, are blocky or rectangular in shape. Other minor constituents of granite include small amounts of dark silicates, particularly biotite and amphibole, and sometimes muscovite. Although the dark components generally make up less than 10% of most granites, they stand out visually and give granite its speckled appearance. From a distance, most granitic rocks appear gray in color. However, granite that is composed of dark pink feldspar grains exhibits a reddish color. In addition, granites commonly exhibit a porphyritic texture. These specimens contain elongated feldspar crystals a few centimeters in length that are scattered among smaller crystals of quartz and amphibole. This massive granitic monolith located in Yosemite National Park, California, was once a molten mass deep within Earth. Smart Figure 4.13 Rocks contain information about the processes that produced them. Watch Mobile Field Trip, Ice Sculpts Yosemite. Did you know? During the Stone Age, volcanic glass was used for making cutting tools. Today, scalpels made from obsidian are being employed for delicate plastic surgery because they leave less scarring than steel scalpels. The steel scalpel has a rough edge, where the obsidian scalpel is smoother and sharper, explains Lee Green, MD, an associate professor at the University of Michigan Medical School. Rhyolite. Rhyolite is the fine-grained equivalent of granite and, like granite, is composed essentially of the light-colored silicates. This fact accounts for its color, which is usually buff to pink or occasionally light gray. Rhyolite is fine-grained and frequently contains glass fragments and voids, indicating that it cooled rapidly in a surface or near-surface environment. In contrast to granite, which is widely distributed as large intrusive masses, rhyolite deposits are less common and generally less voluminous. The thick rhyolite lava flows and extensive deposits of volcanic ash in and around Yellowstone National Park are well-known exceptions to this generalization. Did you know? Although Earth's upper mantle is often depicted in diagrams as a reddish-colored layer to show its high temperature, its color is actually a dark green. But how do we know it is green? On occasion, unmelted fragments of mantle rocks are brought to Earth's surface by rapidly rising magma and are ejected from volcanoes. These mantle rocks, called peridotite, are composed mainly of olivine, which, as the name suggests, is olive green, and pyroxene, which is blackish green. Obsidian. Obsidian is a dark-colored glassy rock that usually forms when highly silica-rich lava cools quickly at Earth's surface. In contrast to the orderly arrangement of ions characteristic of minerals, the arrangement of ions in glass is unordered. Consequently, glassy rocks such as obsidian are not composed of minerals in the same sense as most other rocks. Although generally black or reddish-brown in color, obsidian most often has a chemical composition that is roughly equivalent to that of the light-colored igneous rock granite. Obsidian's dark color results from small amounts of metallic ions in an otherwise relatively clear, glassy substance. If you examine a thin edge, obsidian will appear nearly transparent. Pumice. Pumice is a glassy volcanic rock with a vesicular texture that forms when large amounts of gas escape through silica-rich lava to generate a gray, frothy mass. In some samples the voids are quite noticeable, whereas in others the pumice resembles fine shards of intertwined glass. Because of the large percentage of voids, many samples of pumice float when placed in water. Oftentimes, flow lines are visible in pumice, indicating that some movement occurred before solidification was complete. Moreover, pumice and obsidian can often be found in the same rock mass, existing in alternating layers. Most samples of pumice will float in water because they contain numerous vesicles. Figure 4.14 Pumice, a vesicular igneous rock. Intermediate igneous rocks. Andesite. Andesite is a medium gray, fine-grained rock typically of volcanic origin. Its name comes from South America's Andes Mountains, where numerous volcanoes are composed of this rock type. The volcanoes of North America's Cascade Range and many of the volcanic structures occupying the continental margins that surround the Pacific Ocean are also of andesitic composition.